Okay, so we're gonna say a few words. Welcome, everyone. Today we have the pleasure to have Professor Boris Bukh from Carnegie Mellon. Actually, when I made the poster and advertise it online, many people are excited to have you here, including many students from China, from different universities, and also from Korea. So Professor Boris Bukh will tell us how to use algebraic methods in combinatorics. Okay.
Thank you again, and it's great to be here. Many thanks for the invitation. And so far, I'm enjoying my visit, and I hope to make this summer school this fun for you. So my plan for the lectures is to cover a couple of topics. So the first we'll start with extrapolation. And we'll see. Then we will. I'll talk about some algebraic constructions. It's extreme one, small constructions, and then I plan to do the last lecture on the slice rank again. So these are variety of techniques that was somewhat different in spirit, but it should probably give you some taste of variety of algebraic techniques. And again, if people have questions, I'm happy to go on a tangent and so forth. I'm here for you, so it's not like like preset fixed thing. So, and it also means please, if you have a question during the talk, or you have a comment or anything, or something I say does not make sense, or you cannot hear what I'm saying, or what my handwriting is deteriorating point of illegibility, just make some kind of motion, a sound, something attract your attention, so that we don't get all lost together. Okay. So that's the plan. Okay, so let's start with the extrapolation part. So I want to start this story with the problem of joins. So first of all, let me tell you what's a join. What's the setting? It's a problem in discrete geometry. So you've got a bunch of lines. So you have n lines, and for this particular problem, I will stay in the Euclidean space, so R to the d, and we're going to be interested at the intersection points of these lines. Okay, well, on one hand, of course, it might happen that every two lines intersect. It's fairly easy, right? Imagine you're on a plane, you just draw n generic lines. You can easily make them all intersect pairwise. You can get basically quadratically many intersection points. And if you go to higher dimensions, you can still have quadratically many intersections simply by just let's just put all the lines in the same plane, and we'll still have that many intersections. We want to have a look at the intersection points which are kind of more interesting, d-dimensional. So one way to try to make sense of this is to say, well, we want to have d lines intersecting at a point. Okay. Well, unfortunately, this does not really change the answer that much, because what you can do, you can have, say, a grid. Okay, so this is, and then you can have diagonal lines. Say, this is an example. Okay, so now at every point there are three lines meeting. There are n, say, vertical, say n over 3 vertical, n over 3 horizontal, and something like n over 3 diagonal, and lines. And again, it's still kind of not interesting. It's not really a three-dimensional example if you imagine this sitting in the free space. So a joint is one way kind of to formalize the idea of you want to look at the d-dimensional intersection points of these lines. So a joint is a point where you see d different directions. So definition. The point B is a joint if there are D lines from L1 LD through that point such that the directions of these lines span R to the D. So there are, just look at directional vectors, there are D vectors, and condition they must be linear independent vectors. Oh. All right. And so the problem of this is okay, you have n lines, how many joints can you have? There is a now natural kind of analog of a grid. If you think of 3 dimensions, you might imagine is you have a grid of lines. So just basically take points to be okay, actually probably I should say a word. The bracket annotation, sorry, I should probably say that will always mean the set 1 through M. So this is just a grid with the side length n to the power 1/3. Okay, I'm ignoring the floors and ceilings and whole lectures of this floor, replaced by floor or something if you want. So this is a grid, and then they're looking at the lines that are parallel to the axis. And there are sorry, S squared. Oh, my apologies. There are n lines in each direction, because if I'm say looking at x direction, I have n square root by square root and grid, and looking all the lines through that grid. And so there are 3 n lines, so 3 n lines total, and each of these points is a joint because there are 3 orthogonal directions going. Okay. So okay, I was afraid of this question because I'm horrible at drawing pictures, but since you're asking, I'll have to do it.
Oh, it's not parallel.
Yeah. So basically, so we have basically, so if you take a point, basically it looks like there's a line going in the x so y direction. The one going x, and there is another line going in the z direction, right? So okay, so that's like this.
Okay.
Yeah. So for every point of this grid,
Because it's a square root of h times square root of h parallel lines.
yes. So total, yeah. So we'll get n lines going up, n lines going left, and n lines going. Yes, thank you. Okay. Right. Okay, and all right. So here is a theorem which says that this actually basically the best construction. So if and lines in R to the D, then number of joints is no more than some constant, depending on which I will not pay too much attention right now, some constant to the power n to the d only. So just it's a dimension 3. That's a 3 halves, which is matches exactly this construction. Right? And in general, to get this exponent, you do exactly the same thing in higher dimensions, right? You basically look at the grid, and you look at all the vertical, horizontal, and whatever the directions, lines there are, and you're going to get this is the construct bound you're going to. All right. The constant we'll obtain won't be the constant from here, actually, partly because this is not the best construction. Maybe let me just make a side remark right here on what the better construction looks like. Looks as follows: is you take M hyperplanes in general position, so just so that they, and then take point P to be the all intersection points of D planes, and set of lines all intersections of D minus 1 planes. Now, if you crank the algebra, you will see the constant you're going to get from this construction is going to be better. Okay. And turns out, actually, you can there's some techniques that we're going to discuss later. Okay, some translation of which will not. Actually, you can show that this is the best. This was recently shown by Chow and Yu. Again, but we will not see this proof in these lectures. But some of the ideas we discuss later, we'll go into the proof of optimality. Okay, anyways, let's start with this proof of this first result. All right. So what we will do, we know that it suffices to find a line which contains few joints to prove that there is a line with few joints, so some constant n to the sorry. Okay, let me just give it a second. Thank you. With okay, number of points to the power 1 over the joints on that line. So, okay, so my P is the set of joints, and I'm saying it's if I can find a single line which has few joints, I'm done. Why? Because I can just induct. I can just remove that line. Okay. This might kill at most as many joints. Now by induction, I mean, or on the number of lines, I have my bound, and then I'm just apply it again, again, and again. Okay. So that will be enough. Okay. Okay, so what do I do if I cannot find such a thing? Well, yeah, let's go for contradiction. I cannot find such a line. The idea is kind of weird. I'm going to find a polynomial vanishing at all the joints. Okay, so since this is what we're going to be doing quite a lot, let me just write this as a lemma. So if I have a point set P in R to the D of size strictly smaller than E plus D use D, then there is a polynomial And again, when I say polynomial, I mean polynomial in z variables. So polynomial in z variables, which is vanishes on P. So if you it's if you restrict it to P, it's 0 at every point of P. And it's not a stupid polynomial. So it's not the 0 polynomial, because clearly I can just take a 0 polynomial. Okay. We go into plan B. Okay. So and F is not the 0 polynomial. Sorry, did I miss something?
Maybe the degree.
Thank you. And the degree, this is important, is at most capital. So, all right. That's good. So we want to find the polynomial. Okay, alternative. I tried getting the blackboard up, but it's. Oh, wait, it managed.
That's a reason.
Now we know. Eraser stuck in.
Okay.
Oh, there's one technical issue. Our camera will sense your motion. So if you get past this point, the camera automatically moves to this
Okay.
point. So
I
it's
will
a safe zone.
Okay. Okay. Please shout at me if I try to go there. Okay. All right. We are back. Okay. We are looking for polynomial. It has d variables, degree no more than capital D, and it's got to vanish at those points. We want to find this polynomial. We will think about this as a task of finding coefficients of that polynomial. So I'm going to need some notation to write the coefficients of this polynomial. So I'm going to write f. Okay, so of x. So x is a vector, right? So x is a vector of x's as the sum of c alpha x alpha. Okay, where again, I said I think x is the vector of the indeterminates. C alpha again are some real numbers which you want to find right now. Alpha.
So alpha is also vector.
Yes, exactly. Alpha is a vector. So this is just a bunch of integers, well, non-negative integers. And I want basically the degree to be at most d. So the L1 norm is at most d. I will just bars. And then this notation is just a multi-index exponentiation notation. It means this. So this is just a concise way of writing polynomials in many variables, because if I were to not to use it, I would need to write basically this expression here and like huge number of indices here, and which is kind of going to be bearable, but later we'll have expressions with involving several of the indices and so forth, and it's just going to save us a lot of time just to have some concise notation. All right, so I want to find coefficients of this polynomial C alpha so that this condition holds. Okay, so I'm going to think of C alphas as a vector of unknowns. So this is what I want to find, and how many of them there are? So what's the length of this vector? Well, it's the number of alphas. So that's sum up at most to D. How many of them there are? Speak up. I can't. No, speak. Speak. No, not. This is not good enough.
Capital D plus small d, choose small.
Yes. Yeah, so that's exactly how many of them there are, right? So, I mean, we are choosing again, it's like we can basically it's usual kind of partition problem, right? You know, basically we have you can think of basically we have of alpha 0, which basically equals to D minus this, and we're partitioning the capital D into the D possibly empty D plus 1 possibly empty parts. And this is the fairly familiar formula. Okay, so we have that many unknowns, and what are my equations? So I want to have conditions that F vanishes at every point of P. The conditions are that F is equals 0 for little p index capital P. Well, what is that? That's that become C alpha, right? P to the alpha equals 0, right? This is, if I just plug it in, this is what my condition becomes. This is linear in C alphas. So I have a bunch of linear equations in C alphas, and furthermore, I know so these are linear equations, and not only linear, the right hand side is 0, they're homogeneous. Equations. And there are exactly as many equations as there are points. Now back to our condition here. Did I step behind that? The number of points is smaller than the number of variables. So we have system of homogeneous linear equations. There is going to be a solution. Is a non-zero solution, which is exactly the same as saying there is a polynomial. Okay, so that's that lemma. All right. Good. So we found a polynomial vanishing. We can now find a polynomial vanishing at all points of the proof of the joints theorem. Okay. We can find, so let F be a polynomial vanishing at P such that, well, it's non-zero, and degree, well, we know the degree of F we can take to be right. Well, we just need to find take a degree so that this expression here is bigger than number of points. Now, this expression here, can people just switch it? This expression here, if dimension is fixed, and remember, we are, for now we're thinking of fixed dimension, like dimension 3, then this behaves like d to the power little d divided by d factorial. Well, plus some lower order terms. Okay, so this is basically behaves like this power of, so I can find a polynomial whose degree is some constant, to the power 1 over. Because this is how things. All right. What do I do with this polynomial? Well, I'm going to look at every line of my set. So if Li is a line of it's a line in our set, I'm going to consider the restriction of F to L. So we consider restriction of F to this line. What it means, we are looking at some, if you parameterize L as the set of all the points of the form A plus BT in BT, we are looking at this polynomial in a single variable, like we're just going along the line, it's a single variable parameter, and we are looking at this one variable polynomial. So this one variable polynomial vanishes at every joint of P lying on this line. And by assumption, there are quite a few of them, because remember, we're starting with assumption that no line contains few joints. So F vanishes on at least CD P1 over D points. Okay. Oh, I'm sorry, I forgot to mention, we should probably, I said it on this step before. When we found that polynomial P over there, I can assume as well that polynomial found is the smallest such polynomial. So smallest degree such polynomial. So I should have said here. So I can basically say mean without this generality, F is smallest degree such polynomial. But I'll be doing induction, so it will be as well. I can just say. All right. Okay, so I have a polynomial F vanishing on this many points of the line. Its degree. Now, degree of this single variable polynomial, right? So this is degree just as of polynomial as a polynomial of T. Well, it's no more than degree of this whole polynomial in D variables. And it's, by our assumption, it's at most this much. So we have a polynomial of small degree which vanishes at many points, there is only one conclusion we can draw. It's a zero polynomial. So f a t is zero. Now, okay, so this is a quality of polynomials. Okay, let me just make this right. This is equality as equality of the polynomials. Good. All right. In particular, the derivative of f in this direction of this line is going to be zero. So if I'm going to be vanish identically on the line, of course it means if I'm going to take a derivative and along this line, it's going to be zero. So it's going to be zero if vi also if it's so I use b. So b is the direction, right, of this line. Okay, so this is just for one of the lines, but this is true for every line. So let's now look what that means for a typical joint point. So at every joint point, there are d linearly independent directions. Let's call them V1, VD, in point P. Such that if I look at the derivative of f in this direction, evaluated at the point P, they're all clear. So that means, since these directions span the R to the D, it means if I take the direction derivative in any direction at this point is going to be zero. So it means for every direction D, okay. Which of course means, I can just look at the say ordinate directions, x1 through xz. So I'm going to look at the, so this is just this vector. So this is going to be zero. All right. But, well, how can it happen? Well,
So it's 0 and P.
this is
For complete 0.
so this is 0 as right on P. Thank you. This is 0 on P. Okay. Now, if one of these polynomials here is non-zero, so if one of this, so some of these polynomials might be zero polynomials, some of them might not be, but let's say if there is one which is non-zero, then is a polynomial of degree strictly less than degree of f, because I took a derivative of it in some direction. Derivative drops a degree. It vanishes on p, and it's non-zero polynomial. That's a contradiction to the how I constructed f. It was the smallest degree polynomial that's non-zero vanishing at p. It cannot happen. This would be contradiction. So at this point, I am done. But the only way, so well, hence, and that can happen. So all the derivatives are zero, but that implies that f is a constant, but it has to vanish somewhere, so it's f is zero. It's contradiction. That's all. So so the key step, I want to basically point out before we break, it was this extrapolation step. So namely, when I was on the line, let me just try to locate it. I was on the line. I think it's line. Yes, it's right here. I took a line, and I vanished a bunch of points on the line, and then I concluded I must vanish in the whole line. So I extrapolated the values, so I knew the values at some points on the line. I extrapolated other values on the line. So this was essentially the key step, and the geometric structure allowed me to do that. And we're going to see some more examples, and again more sophisticated examples after the break. Okay,
So we will have a 5 minutes quick break if you want to grab a donut or want to.
Okay, I'm sorry to distract you from your donuts. Let's continue. Quite a few people came afterwards and asking questions about this step. So let me just basically maybe spell it out for benefit people who were didn't come to. So the main step was that the degree of this partial derivative was smaller than the degree of f, and this partial derivative was 0 on p, and this by minimality of f, right? It was polynomial of smallest degree which vanished on p. That implied that this partial derivative was the zero polynomial, and for the course with the gradient is 0, and therefore the polynomial is constant. Okay. All right. So let's now turn to a different problem. So that's a Kakeya problem. So what's the problem? First, let me start a bit maybe history. So the story starts with Kakeya, who was a Japanese mathematician, and in 1917 he asked the question about turning needle in a small set. So okay, imagine this is a needle. Okay, and you're trying to turn it around. Okay, so here I turn it around. And as you can see, I can clearly turn it inside a disk, and he wanted to find maybe a sort of smaller area inside which you can turn a needle. I think, looking at his paper, it's like what he meant probably is a convex set, but we are not going to be talking about convex sets. The problem, the way we understand it now, without convexity assumption. So if I'm not not assuming convexity. So if I'm not assuming convexity, for example, I can start here and do some kind of thing like this, for example. Okay, so coming up, I'm going to figure like this, right? So this is not convex. So the problem was, in some sense, solved in 28 by Bukh. So first of all, let me just maybe we who show that you can turn a needle in a set of arbitrarily small area. So as small as you please. So again, it seems to be a solution, but it can, sometimes more kind of refined problem is the following. So if you if you take a set inside which you turn a needle, of course it will contain line segments or needle in every single direction, because as you turn, you know, for every direction there's no position of a needle pointing in that direction. And so the modern kind of definition of a Kakeya set in Euclidean space is exactly that. So a set K, it's like, okay, so this is K is in R to the D, is Kakeya. If K contains a line segment, say union line segment, in every direction. So so the result of Bukh, which implies that you can make the set to be of arbitrarily small, well, area in the plane, and more generally, arbitrarily small d-dimensional volume, d-dimensional measure in RD. Okay. However, well, as we mathematicians like to create problems for ourselves, that's not end of the story. Because it still does not fully answer the questions: how small can this set K be? For example, if I'm in, say, R3, if my dimension is 3, can I find such a set which is only 2-dimensional, for example? So the big open problem is how small can the dimension of a Kakeya set be? Okay, I won't talk too much about this problem as stated. The only thing I want to say about it is first, there are various notions with dimension. There's Hausdorff dimension, Minkowski dimensions, various several versions of that. There are some versions with maximal functions and even more, which I mean, this is going to be a separate, not even mini course, big course to discuss all of that. And basically it's open for all of those. So there's not a single notion of a dimension for which this is not open. And it's known to be, so conjecture is that dimension has to be a full dimension. So even though measure could be 0, it cannot be a lower dimensional set. This is known in dimension 2 and it's, well, open.
Can you always measure the dimension?
Yeah, again, there are various notions of dimensions. Let me just give you some kind of idea of what, how you, for example, can measure a dimension, one of the ways. So say, imagine you have a curve. Okay, we should agree that it looks one-dimensional. And one way I can kind of quantify this, imagine I'm trying to cover this curve by little balls. Okay, so this is like this. And I can now look at the total size of these balls. Well, if say, so again, maybe say epsilon, let's say covering only by epsilon balls. Let's make it simpler. I look at epsilon balls, I'm trying to cover by epsilon balls. The number of balls needed if it's a line is going to be something like length times 1 over epsilon, roughly speaking. If it's a nice curve, we should agree on that this is going to be true. Imagine now I have a triangle, a solid triangle, and I'm trying to do the same exercise. I'm covering it by little balls. Okay, I'm getting tired, but you're getting the idea. Okay. So the number of balls needed is going to be some kind of constant which relates to the area of the ball times 1 over epsilon squared, because each ball covers area proportional to epsilon squared. And so you see, we think of the line as one-dimensional, and this is epsilon to the 1. We think of a triangle as two-dimensional, and this is epsilon squared. So you can guess what my definition of a set of dimension 3/2 is going to be. Okay. Again, once you actually get into it, it becomes slightly technical, because, for example, as you let epsilon go to infinity, this exponent might not exist, limit might not exist. So you might want to do lim super lim inf. Turns out, for example, a slightly nicer notion works. You get a slightly nicer option if you allow balls of different sizes, but you should weigh the smaller balls differently than big balls. Okay. It's a separate subject. I don't want to delve into it right now. But rough idea for some of the things is basically this. Yeah. All right. So this is open, and we are not going to solve it today. Instead, we're going to look at the more combinatorial version of this problem. And so the problem, analogous problem over finite fields, and we are going to replace this real number R, this field R, by a finite field. And the reason we are doing it, well, for other than just making more problems for ourselves, is because two reasons. One, for a long time it was thought, and it's still, maybe some people are still optimistic, that if you could first solve the problem in a simple combinatorial setting, then you can take the techniques there and transfer to the real problem, like this. And again, this problem has a bunch of applications for harmonic analysis, and so people really want to solve this. And basically, at the time, time being like 90s, everybody thought about, because all techniques that people knew how to make for this kind of problem, all the kind of progress, they transferred to the finite field setting, which I haven't yet explained to you, but I'm going to do it shortly. But it became simpler in that setting. So this was kind of nice toy model setting. So this is one reason. And the other reason, it turns out that this problem I'm going to tell you, some more generalized version of it do have some applications, for example, in computer science, construction of randomness structures and similar things, which again, I will not talk about because we don't have time for those kind of things. Okay, so let me introduce now finite field Kakeya problem. So this is going to be analogous. Yeah. Problem. All right. So what's my definition of a Kakeya set? So a set K. Now I replaced R by a finite field with Q elements. I will call it Kakeya if it contains a line in every direction. So let's go here. Line in every direction. Okay, so let me just spell out what that means. That means for every direction, so every non-zero vector B, there exists some line. So that the A, that's this line. Is inside. So this is the equation of a line in direction B with a starting point A. Okay. Know that the lines in the finite field has a finite, just finite. They have only q points. So it's kind of analog of fixed length line segment. Okay, so this is the definition of what Kakeya said. And now, what's an analog of dimension? Okay, we don't have any the small round balls anymore, but we can. What's our smallest objects? Our smallest objects are points. So we're going to cover our set by points. Well, in other words, we're going to count how many points does our set contain. Well, and how should we think of dimension? Well, a line in FQ has q points, right? A plane has q squared points, etc. So with biology, we are going to think of a set containing q to the d points as d-dimensional. And a d-dimensional space has q to the d points. So it's natural to think dimension basically essentially logarithm of the cardinality of the set. Okay, so I'll put it in quotes. So dimension is logarithm of base q of the cardinality. Okay. So now let's me present you the theorem which we're going to prove next. And this is a solution to Kakeya problem in finite field. This is due to Dwyer first. So Kakeya set Kakeya set in F to D as this D plus Q D that was my minus one minus one is minus one points. Okay, so this quantity here is approximately q to the d divided by d factorial. Again, we are thinking of dimension fixed q going to infinity. So that's so this is basically for large q it scales like q to the d. So it's d-dimensional set of measure 1 over at least 1 over d factorial. So actually, in a finite fields version of the Kakeya problem, it's gonna we see that we cannot actually get an analog of ECOPRO construction. A set will have actually positive measure, at least 1 over d factorial. So it's actually quite different. And actually, a proof we're going to see next does not, well, as far as anybody knows right now, generalize to the case of the Euclidean Kakeya, so to the R to the D. I mean, people have extended some results to R to the D, but conjecture as a Kakeya problem is still okay. All right, so let's prove this. Here's proof. We are going to construct a polynomial again, so which vanishes at k. So let f be a polynomial vanishing on k. Oh, and again, so what's the degree of this polynomial? Well, if this result were false, we would get a polynomial of degree less than q minus 1. So this is k is actually smaller. Let's now look at components of f of different degrees. So we're going to write, say, capital D, it's the degree of f. Okay, so it's going to be less than this, but I don't know what it is. It's some number. And I'm going to write f as the sum of the homogeneous components. Okay, so in other words, this term here collects all the monomials of degree capital D. This term here, all the terms of degree D minus 1, and so forth. So Fi is the homogeneous component of degree I. All right. And since capital D is degree of f, the leading component is non-zero, because I'm assuming this is actually D. Now I'm going to use my assumption that there is a line for in every direction. So let's just okay. So pick a direction. By the assumption, there is some vector, so that there is a line starting from that vector, is completely contained in K. And therefore, f is going to vanish in it. F very strict to this line. Okay, 0 for every T F. Okay. Now, so this, so again, we have this expression here is a polynomial in a single variable t, and it's of degree. Again, degree in t. Well, it's at most the degree of f. It's at it's small. And it's but it vanishes at many points. Therefore, it's got to be a zero polynomial. So this was equality, pointwise equality, but we deduced equality of polynomials f q. Now, let's go back looking at the components. We are going to look at the coefficient. Okay, so let me just maybe make a small aside. Notation. At c to the I of and say g of t is the coefficient of t to the I in g of t. So this is notation. So I'm going now to look at the highest degree coefficient of this.
Boris, I have a question. So do you need degree f to be strictly less than q minus 1 or at most q minus 1? At least from
I don't say less, but I mean, currently I only use less than or equal. Let me think. Maybe not. Maybe I don't need minus 1. But I need to think through this. But I mean, it's not going to make a difference for the main thing, but I don't think I'm using it. No. I think I would. You're right. We could probably get rid of it. Sorry. Yeah. All right. I'm going to look at the coefficient of t to the power capital D. So the highest degree coefficient. Well, it's going to be just coefficient of t to the d f plus bt plus the coefficient of t to the d in the f with b minus 1 plus etc. Now, the good thing about this expression that this term starting from this one actually going to be 0 because I mean these polynomials have degree strictly less than the capital D. I mean I'm not going to get anything of degree D there no to the D terms. So this is actually all 0. So the only thing will survive is this. Okay. This. All right, so this is going to be the coefficient in t to the of f d a plus bt. All right. So what does this thing look like? Well, let's just write it out. So say my FT of x is just the sum of some coefficients of x to the alpha. Okay, and these are all terms of degree exactly d. Then when I look at this, I'm going to get a plus bt to the alpha. Now, and then I'm going to expand this using binomial theorem. Okay, we're just going to expand everything, go open up all the parentheses. Remember, this is multi-index notation, so actually really it's a product of little d terms, one for each coordinate, and I'm expanding all of it. It's a big mess. But the only thing I want to tell about this mess, is how am I going to get t to the power capital D. So when I expand this mass, I have a choice each time. Do I choose A or B times t term? Well, I have to choose the B times t term because otherwise I'm not going to get enough powers of t. So the only way I'm going to do it if I'm just ignoring this A completely. So I'm looking at this thing, and I'm looking at this. That's going to be exactly the same as the coefficient of this of BT. I just ignore it. All right, that's a progress. So now remember, this was a homogeneous polynomial. So that means if I take t multiplied by if b multiplied by t, it's the same thing as basically taking t out to the appropriate power. So this is going to be equal to t, since this homogeneous of degree capital D, t to the d times f of t of b. This is by homogeneity. All right, good. Now remember, this was 0, because this polynomial is a 0 polynomial. We are looking at a particular coefficient of a 0 polynomial. It's a 0. So conclusion is that this number is 0. All right. So what we just learned is that polynomial f sub capital D is 0 everywhere. For every value of D. So let me just write it. F of D vanishes on F Q up to the D. Well, for all, again, if B is arbitrary non-zero. But what happens for 0 vector? Well, remember this polynomial is homogeneous. So the constant term is going to be 0 unless D is equal to 1, unless degree is 1. So in fact, it's going to vanish everywhere. So if D is not constant, then f of 0 is 0, and so we actually have it vanishing everywhere. So we have now polynomial vanishing everywhere, and it's polynomial of small degree. We now want to conclude this is a 0 polynomial. So fine, make a lemma that if I have G I should probably G and G of B 0 all B in this, then G is the 0. So this is a generalization to higher dimensions of this fact that if I have a polynomial in one variable vanishing on too many points, and it's sorry, and so I have degree conditions. My apologies. And degree G is got to be less than Q. Then this is 0. Okay. So let's prove this. Induction on the dimension. The base case d equals 1 is just the usual one variable case. I mean, we're all familiar with it. I won't dwell on that. The induction step, I'm going to write x prime as as the vector of the first d minus 1 coordinates. I'm going to write my polynomial G as a polynomial x to the d with coefficients in x prime. So this is the sum of x to the d to some power I. I goes from 0 to q minus 1 of some coefficients. Now, and these coefficients are themselves polynomials in x. So, in other words, I have just collected all the monomials where power of x to the d is I into single term, which are called ci. Okay, now let's look at some value of x prime. So consider line where x prime is equal to something, some a. So this is a line where I'm just varying the last coordinate xd. On this line, so in other words, when I'm looking at this. This is vanishes on all q points of q. So for every value of xd, by one-dimensional result, this is the 0 polynomial. So this is the 0 polynomial. Now this happens for every value of a. So that means these things that the CA alpha x prime is 0 for all a. And now we're going to induct because CI is a polynomial in d minus 1 variables. Ci prime is a polynomial d minus 1 variables. And of course, its degree is smaller, it's not bigger than degree of G. And so by induction, it's the I is 0, and then the whole polynomial. Okay, so so remember why we had this lemma, because we had this polynomial vanishing on all of f. U to the d means this is 0. This is by the lemma. But that's not okay, because we just agreed that f d is non-zero. Okay? And that's a contradiction. And what we're contradicting? We're contradicting the assumption that k was set so small that we could find a small degree polynomial vanishing. Okay, that's the proof. Now, so you can think of this proof as extrapolation in two ways. I want to point out basically what commonality what we did. On one way, of course, we were basically have the same step. We know we have f of vanishing many points, f is 0. But we can also think of it as extrapolation. We are in the same fashion as before. Before we had f was 0 the points of the joint points, and therefore it was 0 in between, and it allowed us to take the reduction derivatives. But here it seems to be not having the same kind of inference, because we are having f vanishing a bunch of points. It's all the points on the line. There are more points, like what are we extrapolating to? So we are extrapolating to, and what we are extrapolating to points at infinity. So this is, let me just make a digression to that, because it's, I mean, though proof is complete as we've written it, it is sometimes helpful to think geometrically. So I do want to point this out. So here is a small crash course on projective geometry. Okay, so okay, we say, okay, so okay, so we have a plane, right? And say there are lines in it, right? Here, it's nice to, so this is, it's nice to think of the plane as sitting inside some usual, yeah, the pictures I'm drawing in the usual opinion pictures, by the way. Oh, but algebra does not change. It's nice to think of the plane as sitting inside a bigger space, projective space. So the name comes from basically, well, the original was developed by artists during Renaissance. So imagine you have, okay, the actual plane, and you have my drawing skills are going to be strained by this, right? They have some kind of road, right? So what happens? We all recognize this picture. There are two lines. I mean, this is two sides of the road. They're parallel. I mean, if you go, you can see, okay, they don't intersect, we hope. But they look like they're meeting at a point in the horizon. And I mean, if you also there's the third line, which is the divider line, also meets at the same point. So basically, this parallel line meet all at the same point. So the way you make projective geometry informally is you take a plane, and then for each equivalence class of parallel lines, you add one more point. So if you imagine is the point where all these lines meet, you just add it. Just so your set now becomes a plane plus a bunch of extra points, one for each set of one for each direction. And then you get this, but you know, like, so this will be some another point and so forth. All these points, we call points in infinity, they themselves form a line. Okay, so this is projective geometry. Algebraically, it's easier to describe it algebraically. So algebraically, you can think of the usual plane as so say as living inside a plane z equals 1 inside three-dimensional space. So this is the plane. This is the plane, say, a copy of R2 inside R3. There is an origin somewhere here. So every line, for every point corresponds to a line through it. So for every point, there is a line through it. And so point corresponds to the line for the origin, and lines correspond to planes through the origin. And then you can now see where those lines which parallel meet, they meet. So these are lines correspond to planes, they can meet at the line parallel to this plane. Okay. I know this was a crash course, but it should mostly motivational or refreshing for people who have seen already projective geometry. The point is, what we can think of motivationally, that these polynomials are defined not just on the plane, this plane, but on the whole projective plane. So what you are doing when in this step is you look at the this line, part of the line which is in this study, our usual plane, and we extrapolating onto the points at infinity. This is okay. I don't expect people who haven't seen projective geometry to understand what's happening right now. This is mostly for people who have seen some projective geometry. Okay, as a comment. And so this is what the look. And so then we know that it vanishes at the line infinity, and then basically we complete the proof the way we did. Okay, that's the okay. So I think I have between 0 and 5 minutes. What's the right number?
Sure, any number you want.
Be careful. Okay. So I think let me just basically mention one thing. So next lecture, we are going to look at a refined version of this method of vanishing and extrapolation. But for now, I want to basically give you tell you a construction for the Kakeya problem. So which is basically tell you what is our job for the next one. Okay, so recall what we just showed. We showed that K is a Kakeya, then the size of it is about roughly speaking, yeah, I will ignore lower order terms, has measured at least 1 over d factorial. And let me show you a construction of Kakeya set of size, which is not quite as small as this, but reasonably large, reasonably small. So, so there exists Kakeya set of size q to the d divided by 2 to the d minus 1. Again, plus lower order terms, which I'm going to. Here is the set, and we're just going to write it down. So first I'll construct a set which I'll call K prime. maybe not. Let's go. The and the set is going to be AI plus A and D squared. I should make sure I'm not going to mess myself. I'm very sure. Yes. AD squared is a square for all so basically, so now again, in other words, there is this vector of d minus 1 coordinates, and there is a d coordinate kind of special, and we are looking at the add one of this to the square of this and condition that this sum is a square in FQ squared. Now, the size of this set is q to the d minus 1. It's really need to see if I fix any value of AD, right? How many ways can I choose the A1? Well, there are q plus 1 over 2 ways to choose it, because this is how many values are squared in FQ. And how many ways to choose A2? Well, same number. So the size of K prime is q times q plus 1 over 2 at power d minus 1, which I just abbreviate to the q to the d divided to the d minus 1. Okay, and if and if B is any direction for which the last coordinate is non-zero, so not every direction, but many direction, then I'm going to find a line pointing in that direction inside K prime. Namely, I would like to say, so last coordinate will be C, and the intermediate coordinates will be let me just probably cheat and just look it up what my calculations gave me. So B1 squared over 4, B2 squared over 4, and so forth. Okay, so and let's check that this is sorry. I'm sorry, I didn't try it out. Okay, let me not skip. So I want to find line. So what's the line? Line in direction B. So there is going to be B1T A D minus 1 plus B D minus 1T. C, it's okay. Is in K prime if AI plus B I T plus C squared is a square for all T. Okay, so we are going to take AI to be BI squared over 4. Okay, and that's way BI squared over 4 plus BI T plus T squared is equal to the BI over 2 plus the squared. Okay, so the line
Taking
BD to be one, which is fine, right?
Sorry?
In the direction, you just take the last one.
yes, you're
But that's fine. Right? This is-
Thank you. Thank you, Ben. Okay. Sorry, this is way too why I was thinking. Thank you very much. Yeah, so that's by scaling, I can just take BT equals 1, and this is the my line. Okay, so so this K prime contains lines in every non-horizontal direction. And so finally, I'm taking my K to be K prime, the union a horizontal hyperplane. So the so this second part contains line in every horizontal direction. And total size is still basically the same because this is lower dimension. Okay, so this is a construction. So next time we will see how to show that this construction is almost optimal. We will get bound close by using vanishing to higher degrees. So we define vanishing polynomials at some point. So we'll vanish on a higher degree, and we'll discuss that. Okay, so that's the plan. Thank you for your attention. And of course, if people have questions, I'm still around before lunch. So like no more than an hour of questions, please. Yeah.